Good afternoon and welcome to Quest for February 25th, 2022. Thank you for coming out. We thought another Thursday snow upon us, but we managed to gather this week. Thanks all for coming. To begin our meeting today, Susan Burns will deliver our invocation as well as a moment of silence for the people of Ukraine.
Let's begin with our thoughts, sending our thoughts to the valiant people of Ukraine who are fighting today to defend their capital. If you'll join me for a few moments to send our thoughts. Thank you. I'm happy to provide some words of inspiration today. The interplay of land and water, as well as ice, lake, or stream, is at the heart of our community's history and prosperity. So while Jim informs us of the work of water's long-term frozen form, let's celebrate the liquid. Today's invocation was written by the Right Reverend Christine Hardman, Bishop of Newcastle in York, United Kingdom. Creator God, thank you for the waters of the earth, for the life-sustaining rains, lakes, and deep oceans. Keep us mindful of how precious these are and how vulnerable they are. Help us to work together for clean water and for the sharing of it with those who have need of it today.
Today's paper is presented by Jim Griest. Jim grew up in Fort Wayne, the son of Dr. Walter Griest, MD, and Patty Griest. He graduated from Southside High School, then attended Albion College and Indiana University, where he graduated with a BS degree in accounting from the Kelley School of Business and a minor in economics. Jim is a business development executive with BKD LLP, a national CPA and consulting firm with offices in Fort Wayne and across the country. The firm offers services beyond standard accounting services to include risk management, technology, wealth management, forensic and business valuation services. Jim began his professional career at Summit Bank as a credit analyst in the commercial loan group, eventually landing a role as a trust officer for Indiana Capital Management. From there, Jim embarked on a 25-year career as a private banker for several national, regional, and local banks. He landed his current role where he finds great satisfaction in adding value to clients by matching client needs with professionally aligned solutions. On a side note, Quest member Fred Haig was Jim's junior high school music director, where Fred acknowledged that Jim was an intuitive French horn player. Jim has been a volunteer or board member of a number of area organizations, including Parkview Foundation, the Fort Wayne Metropolitan YMCA Board, the Rotary Club, and he's a past president of the Warsaw Rotary Club, Leadership Fort Wayne, the Kosciuszko Leadership Academy, Macmillan Center for Health Education Board, Science Central Board, Ronald McDonald House, the First Presbyterian Church Foundation Board, the Northeast Indiana Regional Partnership, the Wagon Wheel Center for the Arts Board, and the Kosciuszko County Community Foundation Scholarship Committee. Jim has been a member of Quest Club since 2019, and his paper today is The Effects of the Ice Age on Indiana. Jim?
A couple of things. I'm not sure who that guy was in that bio, but it sounded pretty good. And Fred, I think when you were teaching me, I think you were about 12. Thank you all. It's an honor. It's humbling to be able to present to you today. This has been a fun process. And if you haven't written a paper, you're going to have a ball when you do yours. It's a lot of fun. Reasoning effectively is obtaining, retaining, and using the knowledge, insight, and understanding of subjects that have been discovered, studied, and determined by others. Logical reasoning is the best way to discern for ourselves what was, is, and can be. When we realize that radical changes have taken place on Earth many millions of years ago, and up to and including today, our perception of the Earth and our relationship with it changes before our eyes and in our minds. The land upon which we live is fascinating, miraculous, and humbling. As we look around, some questions may come to mind. Why are there granite boulders out in the middle of farm fields when there's no granite bedrock in Indiana? That's called a glacial erratic. formed in Canada millions of years ago, carried by the glaciers, and dropped by the melting ice sheets. Another question is, what formed our beloved lakes in northern Indiana? The answer, huge chunks of glacial ice driven into the glacial till. When the ice melted, the lakes filled with the meltwater. The lakes in northern Indiana are kettle lakes. Another aspect of this study is the comprehension of geological time, eons of geological time that are difficult to grasp by our minds. After studying geology in college eons ago, I still have a challenging time holding the concept of millions of years in my head. Ocean sediment may build up in one's lifetime by mere inches, but how does one conceptualize the buildup of 10,000 feet of sediment on the ocean floor? Or imagining the spectacle of a mile-high wall of ice, water, snow, rock, and sediment, and the power of it. It has the power to relocate mighty rivers hundreds of miles. The ancestral Ohio River, once called the Taze River, ran through central Ohio, then on to Bluffton, and then to Peoria, Illinois, where it turned south, draining into the ancestral Mississippi River. The sheer power of the ice sheets shoved the river 100 miles south to the present-day Ohio River and bulldozed it westward nearly 90 miles to present-day Mississippi River. Imagine. Virtually all our daily lives are affected by the facets of the Ice Age. Our groundwater, for example. It supplies approximately 90% of Indiana with all water used for domestic consumption and economic activity. Most of the major aquifers that yield this groundwater are a direct result of glaciation. While many resources regarding the glaciers are available, most focused on the impact of the Ice Age on a broader scale. The effects of Indiana are only a fraction of the huge impact the Ice Age continues to have on our way of life. For this paper, I've narrowed the scope to Indiana as appropriate, then broadened the scope for larger context and further understanding. This paper is about ice ages and what causes them. It does not address the significant differences between pre- and post-industrial revolution climate shifts. You may find ways to get out there and enjoy these fascinating geological features in Indiana. Pokagon State Park, the Three Rivers right here in Fort Wayne, Clifty Falls State Park, McCormick's Creek State Park, Pokagon State Park, or even one of the Kettle Lakes just a few miles away. There are more. Go out and enjoy. Before the glaciers, the Ice Age lasted over 2 million years. This period of geologic time is known as the Pleistocene, a formal period that began 2 million years ago and technically ended 10,000 years ago. The geological record indicates that major episodes of glaciation occurred as far back as 2.4 billion years. The Carboniferous period, 300 million years ago, and the Ordovician period, 400 to 500 million years ago. Periods of much colder climate marked by major incursions of ice sheets into lower latitudes are a regularly occurring feature of our Earth. The ancestor to the North American continent was straddling the equator after Pangaea broke apart 180 million years ago. Prior to the Triassic period, Pangaea was a hypothetical continent, including all of the land masses of Earth. And when it broke apart due to plate tectonics. The many land masses drifted in these plates, ultimately forming the continental spaces that we know today. At least 4 major ice advances in the northern hemisphere can be discerned from the geological record. Each successive advance tended to wipe the history of the prior advance, much like an oil painting where the artist paints over another piece of work, potentially hiding another masterpiece. The end of the Ice Age was approximately 10,000 to 15,000 years ago, give or take a few thousand years. Between these advances, also known as interglacials, the climate was not far different from our climate as we know it today, even warmer. 2/3 of Indiana owes the landscape of the activity to the vast ice sheets of the glacial advance ending 10,000 to 12,000 years ago. Prior to the Ice Age, Indiana and much of the Midwest was maturely dissected low plateau with hills called knobs, separated by broad valleys. This landscape was not unlike present-day Kentucky or Missouri. All the landscape of the southern third of Indiana is a hint of what the rest of the state probably looked like. Another clue comes from an area in central Wisconsin known as the driftless area, which lacks glacial debris or drift. There is debate among scientists and geologists that the highlands of northern Wisconsin may have deflected the ice lobes around the area, including the Wisconsin Dells with its beautiful streams and majestic cliffs. Another clue comes from the surface bedrock in an area near Delphi, where the outcroppings of a rock dome as part of a coral reef from an ancient sea that formed 400 million years ago when Indiana was covered by a warm inland, brackish sea that stretched from present-day Labrador southward to here. Interestingly, just behind the former Elmhurst High School lies the Hanson Aggregates Quarry. That's another coral reef remnant from the warm inland sea. Remnants of this sea created a bowl-shaped basin once made up of softer rock. Over time, this softer rock became hardened by acidic rains, creating dolomite, an extremely hard rock. These dolomite ridges encircle and are underneath three of the Great Lakes, Michigan, Huron, and Erie. The most famous fragment of this dolomite ridge is Niagara Falls, where the water of the 4 Great Lakes pours into Lake Ontario and then eastward through to the Atlantic Ocean. Another feature of the Indiana geology prior to the Ice Age is the Cincinnati Arch, a geologic arch-like structure 250 million years old. It existed as a persistent low-lying area flanked by inland seas covering a large part of the continent, while connected with the ocean. Bifurcated by a structural saddle, its southern extension is called the Nashville Dome. Northward, the Cincinnati Arch has 2 branches. One tending this direction is known as the Kankakee Arch, the other branch trending north-northeast known as the Findlay Arch. Imagine several layers of beach towels with a series of baseball bats underneath. Sorry, spring's coming, I got a baseball on my mind. It deforms the upper layer of the towels, approximating the anticlines found in southern Indiana. A cross-section could look like a multi-layered wavy birthday cake with multiple layers. After years of erosion, these lifted layers will be exposed one by one, and as that pressure from underneath comes up, it comes up here at this point, and as you can just see it in your fingertips, it starts to expose each underlying layer. And when you see it as how does that, if you think everything is stratified, it actually gets bent up by those ridges. Some regions of southern Indiana have huge deposits of limestone near the surface. Some of the layers of limestone over the years have been subject to acidic drainage that percolates through the soil. Since limestone is dissolved by acids, the landscape includes caves, sinkholes, and even lost rivers, called karst topography, that evolve over time. Many of these areas can still be explored today. The Ice Ages. The Earth is dynamic, with titanic forces that we are only beginning to understand. In geological terms, the grass has never grown under the Earth's proverbial feet. 2 million years ago, the average temperature of the lower 48 states was 56 degrees, 3 degrees warmer than it is today. Over a period of 10,000 years, a blink of an eye in geologic terms, the temperature dropped to an average of 26 degrees year-round, roughly the average temperature we experience here in winter. Scientists are unsure why the temperature changed, perhaps a result of the Milankovitch cycles later described. The change could be attributed to the tilt of the Earth's axis, a variation in the Earth's orbit, and volcanic activity. Even the creation of the Himalayas is suspect, yet that theory is still in debate. Once the snow began to fall, it simply built up layer by layer, year by year, until the sheer weight of the snow began to compact the snow. As the hexagonal snow crystals break down, they become more dense and more compact. The snow eventually turns to ice. By the sheer weight of the ice, it begins to move toward the warmest edge of the ice sheet atop a kind of plastic-like characteristic, yet still made of ice and snow under enormous pressure. Because the snow has a high reflectivity or albedo of 0.85 to 0.90, meaning 85 to 90% of the sun's energy is reflected back into the atmosphere, the cooling cycle becomes self-perpetuating. Sea ice and snow has a much higher albedo compared to the other surfaces, with its albedo ranging from 0.85 to 0.9. This serves to insulate the ice, maintaining cold temperatures and delaying ice melt in the summer. The most severe ice age was 850 million years ago and lasted for 200 million years. So severe that the entire planet was covered in ice, ending when massive volcanic activity caused by tectonic plate movement resulted in the pouring out of carbon dioxide into the atmosphere, which developed a period of warming, melting the planetary ice sheets. They can spot these cycles in ocean sediments and in ice cores of small microscopic animals that kind of trap that atmospheric atmospheric characteristic of the time. Since then, there have been 4 advances of the ice sheets from the north. In between the advances, the climate warmed and the ice sheets retreated northward to Canada or disappeared entirely. These interglacials lasted for a few thousand years. We could be living in an interglacial period today. Some suggest that we are amid such a cycle of change. Some interglacials last 50,000 years, while some last 12,000 years. Indiana's glacial history is complex and incomplete. It's impossible to know with certainty how many times the ice sheets have invaded the state following the very first event. Subsequent ice sheets erase or cover up earlier glacial deposits, producing variations in the geologic history. In general, geologists divide these events and the glacial deposits of the Ice Age into 4 stages, each period experiencing multiple advances and retreats. The Nebraska and the Kansan glacials are not well understood because they happened so long ago. Several events from this stage are known to have affected Indiana, yet evidence has been erased by more recent advances. The Illinoisan Glacier began around 300,000 years ago and lasted 160,000 years. These deposits are exposed at the present-day land surface in southeast and southwest Indiana beyond the limit of the Wisconsin ice sheets. The Wisconsin Glacial, which was the most recent, began about 50,000 years ago. This advance did not extend as far south as the previous stages. It reached as far south as Terre Haute, following a meandering line over to Richmond, and is responsible for the current topography of Indiana. It began to retreat about 20,000 years ago, and by 10,000 years ago, the glaciers melted and retreated into Canada, the start of the present-day interglacial. These interglacial periods are not unlike the weather that we experience today. Some periods substantially warmer, some cooler, yet in all form, the usual land formation processes were in full swing. Sediments weathered to form soils, forests and prairies dominated the landscape, and rivers cut valleys. The ice sheets as a landscaper. The ice sheets of the last ice age were in places 3 miles thick, exceptionally powerful, exceptionally heavy. If you can imagine just a mile-high sheet of ice, it's about 3 minutes after you take off from the airport that you reach 5,000 feet. And that is how thick the ice sheets were in many, many places. It's amazing. The ice sheets carved out valleys, scraped bedrock from Canada, ground out massive amounts of debris as the ice sheets advanced southward. Ice behaves much like water, following a path of least resistance. It's the major factor in geologists, hydrologists, and scientists believing that the initial ice flow followed along the course of bedrock valley systems along the US-Canadian border. As the first of these glaciers moved over these valleys, they carved the soft rock into great basins, shaping the forerunners of the Great Lakes. Advancing further, they bulldozed, carved, filled in, and completely changed another huge valley system known as the Taze Bedrock System. In its day, it was the chief drainage system in eastern North America, with the headwaters in North Carolina, wound its way northward to Indiana near Bern, and then over to West Lafayette. Boiler up, I say that, all of our kids went to Purdue. And westward to near Peoria, Illinois. It then turned south to join the present-day location of the Mississippi River. Today, there's hardly a trace of the once great river on the surface. It's only known by test borings and wells. The ice sheets have so much force that river was forced southward and westward by at least 90 miles in either direction to what was today the Ohio River and the Mississippi River. The ability of water to carry massive amounts of sediment depends on its flow velocity. The faster the flow, the greater the volume carried. Larger, heavier objects are the first to settle to the bottom as the flow as the velocity slows. Meltwater flowing through, over, and away from the glacier deposited the sediment in particle-sized layers. The larger and heavier ones deposited first. Then sand settled, followed by silt and clay. When the glaciers in Indiana started to retreat, they began reshaping the landscape as they moved. A process called calving occurs where large chunks of ice break away from the retreating glaciers. These calved blocks of ice then cut and sink into the outwash plain, carving out large depressions in the earth. The blocks are left behind and melt as temperatures rise and the glaciers continue to retreat. These large depressions that are filled with water from the melting ice by surface or underground rivers are called kettle lakes. Glaciers also carve out depressions to form rivers, streams, and dunes. Many kettle lakes are predominant in Indiana, especially northeast Indiana, most notably Lake Wawasee, Lake Tippecanoe, Hamilton Lake, the Lake James Chain of Lakes State Park, and Clear Lake. A glacier can also deposit its load of sediment directly from the ice without the process just described. Unsorted boulders, sand, silt, clay is all called glacial till, which makes up the middle third of Indiana, known as till plains, which can be very thin to as thick as 265 feet near Michigan City. When an ice sheet remains stationary for a long period of time, end moraines form. They form because the ice within the glacier advances southward until the melting at the leading edge is in equilibrium with the advance of the new ice. When the ice reaches the front edge, it drops all its debris. An end moraine is made of the glacial till that builds up at the glacier's leading edge. Most of the northern third of Indiana is comprised of moraines, notably the Valparaiso Morainal Complex, the Plymouth Morainal Complex, Warsaw Moraines and Drainageways, and the Auburn Morainal Complex. Another feature in northern Indiana are the drainageways that are adjacent to the moraines, notably the St. Joseph Drainageway and the Kankakee Drainageway. I feel the ice move. Counterintuitively, the coolness of the summers is more influential on the life cycle of glaciers and ice sheets. Unless the snow ice can remain on the ground, there's no chance for a glacier to form, no matter how cold the winters are. As the snow builds and begins to compress the hexagonal snowflakes together, the weight of the snowfield becomes denser and heavier. When the ice field builds to around 2,000 feet thick, that's when the ice begins to flow. As they grow in height and width, the sheer weight of the ice depresses the crust of the earth into the mantle. So if you grab a hold of your little globe, if you can imagine just you're deflecting that globe with your thumb or a finger. That's what the ice sheets did to the earth. For every 300 feet of ice sheet, it deflects the mantle by 100 feet. Rates of flow can vary. It is thought that the ice sheets that moved into and across Indiana flowed relatively quickly due to the abundant water supply at the base to lubricate the movement across the landscape. This process is called solifluction, a geomorphic process that involves the slow movement of water, saturated soil down the slope, and usually occurring on frozen subsoil or during freeze-thaw activity. The term originates from the Latin words solum and fluxion, meaning soil and to flow. Solifluction likely fringed every ice sheet that invaded Indiana. Glaciers can be imagined as a kind of rock sediment conveyor belt. Countless cubic feet of bedrock, soil, sediment, debris was scraped from the landscape, deposited down glacier, along with larger quantities of the same glacial content inherited from areas north of Indiana. In fact, some rocks in Indiana came from the center of Michigan with sediments that are magnetically reversed. Earth's magnetic poles were reversed. The most recent record shows the last flip happened during the last ice age about 700,000 years ago. The edge of the glacier is where the ice is always melting, and the environmental conditions near the edge of the glacier were severe. Monsoonal rains and profound freeze-thaw cycles intensified the volatility and instability of the landscape. All this was likely compounded by katabatic winds, cold blasts of air roaring off the glacier as air masses passing over the ice sheets collided, producing its own local weather. Warm, moist Gulf air masses overriding the ice sheets likely created torrential rains in summer and near-constant glacier effect snows in winter. Indiana landscape regions. The landscape of Indiana can be categorized into thirds: the hilly highlands and lowlands of southern Indiana, the central outwash till plains, and the northern moraines. The southern highlands and lowlands in the lower third of Indiana is categorized by 7 different physiographic regions. They all exist because of the bedrock with no glacial influence. Since the edges of the bedrock are arched, the edges have eroded, exposing the edges as one would travel from west to east. Remember that first slide? That's what southern Indiana is comprised of. Some layers of limestone that form karst topography, tending to erode into a low flat plain. Karst topography refers to the type of subterranean limestone cavernous landscapes, as well as the mysterious-looking formations like caves, service sinkholes, and rocky overhanging cliffs because of natural forces. Some layers are soft shales and erode easily. The more resistant layers make up the highlands, while the softer karst topography generally comprises the valleys. The central portion of Indiana is south of a line from Rensselaer to Fort Wayne. to the southernmost advance of the Wisconsin Glacier is made up of the Bluffton, Newcastle, Tipton, and Iroquois till plains. It is broad, gently rolling region of unsorted drift deposited by the ice as it retreated into Canada. Known as part of the breadbasket of America, it owes its birthright to the legacy of the glaciers. The glacial deposits of finely ground fragments of countless rock types and rich soils that have developed on them. Few other areas in the world can match all of these attributes. The northern third of Indiana is moraines and drainage ways. In the northwest, the deposits were left by Glacier Lake Chicago. Most of the area is sandy with some clay deposits. Paralleling the Kankakee River is the Kankakee Outwash Plain, a flat area of sediments carried by the glacial meltwater. Central and northeastern Indiana are moraine complexes with rich, fertile soils, rolling hills, and filled with hundreds of kettle lakes that dot today's landscape. The Great Black Swamp. Thank you, Michael. Where are you? Thank you for mentioning that last week. Lake Erie was the first of the Great Lakes to emerge when North America's Ice Age glaciers began pulling back. In addition to leaving behind Lake Erie, those ice sheets also created the conditions for a nearly 1 million acre wetland complex to form along the lake's southwest coast. The land once covered by the swamp lies primarily within the Maumee River and Portage River watersheds in northwest Ohio and northeast Indiana, right over to the east side of Allen County. The myriad of intricacies and evolution of this massive wetland system might be a great topic for a future quest paper. The Great Lakes, the ice legacy. As the ice sheets retreated into Canada, a very large lake called Lake Algonquin formed, covering an area equivalent to present-day Lake Michigan and Lake Huron. Lake Duluth, the ancestor to Lake Superior, was forming along the western edge of the glaciers near Lake Algonquin, with the southern shore near the present-day shoreline. As the ice sheets retreated even further, Lake Algonquin merged with Lake Duluth to form Lake Nipissing, covering the area presently occupied by the Lake Michigan, Superior, and Huron. When the ice sheets finally disappeared, the Earth's crust that had been deflected inward began to rebound in a process called isostatic rebound. A drainage pattern emerged with an easterly flow which lowered Lake Nipissing substantially until all the lakes settled into the shorelines that we know today as the Great Lakes. Lakes Michigan, Superior, and Huron drain eastward into Lake Erie. From Lake Erie, it flows to the Niagara River, over Niagara Falls, and into Lake Ontario. From there, it heads out to the Atlantic Ocean. Indiana rivers. The Ice Age completely changed the drainage pattern in Indiana. The ancestral Missouri River drained into the northeast into the Arctic Ocean. The ancestral Ohio River was much further north, represented above as the Taze River. It turned southward in Illinois and draining into the ancestral Mississippi River and to the Gulf of Mexico, which once extended into the central present-day United States near Cape Girardeau, Missouri. The Wabash River is the largest river in Indiana, paralleling the end moraines where it passes through Lafayette and Terre Haute, finally draining into the Ohio River. There's a continental divide which is in northern Indiana, just south of Syracuse and Lake Wawasee, separating the southwestward drainage into the Mississippi River from the Great Lakes drainage system to the northeast. The Maumee River, which originates in Fort Wayne at the confluence of the St. Mary's and the St. Joseph. Did I get that right, Ron? It flows eastward, meandering through northwest Ohio and into Lake Erie. What caused the Ice Age? The poles shifted. Continents move around on the Earth on crustal plates in the asthenosphere. The asthenosphere is a zone of Earth's mantle lying beneath the lithosphere and believed to be much hotter and more fluid than the lithosphere. The asthenosphere extends from about 100 kilometers to about 700 kilometers below the Earth's surface. Heat from deep within Earth is thought to keep the asthenosphere malleable, lubricating the undersides of Earth's tectonic plates and allowing them to move. When a landmass travels and changes the flow of tropical waters, from the equatorial regions toward the poles, it causes the poles to become colder, making it more likely for an ice age to begin or become more robust. Most likely, the most recent ice age began when the land bridge between North America and South America formed Panama, ending the exchange of tropical water between the Atlantic and Pacific Oceans, significantly altering the ocean currents. When the currents shift, so do the atmospheric currents. Many other factors contribute to climate variations, including concentrations of atmospheric carbon dioxide, volcanic eruptions, and evolving plate tectonics. I'm going to geek out here for you in a minute. I found an interactive slide that made a lot of sense to me, and I'm not finding it here. Okay, well, that's just fine. Don't worry about it. So what happened is, and if you'd like to afterwards, I can show it to you. But what happened is the pole shifted from the present day to the pole during the Ice Age, which basically shifted the entire Arctic Circle down and over where we are. And that cooling and that shift is what probably most likely was the biggest contributor of the Ice Age. Other factors causing the shifts in Earth's temperatures, there are 3 cycles of variations of the Earth's motion and alignment in space: tilt, orbital shape or eccentricity, and precession. The tilt varies within a few degrees of 23.5 degrees. The Earth's orbit around the sun is not a circle, rather it's an ellipse. It is known as eccentricity. During some eras, the orbit is more elongated than others, producing enhanced seasonal effects and the wobbling motion of the Earth's axis. Currently, the North Pole points at the North Star, Polaris. Yet 11,000 years ago, it pointed to a star in the Big Dipper. This complete cycle happens every 26,000 years. The combination of the cycles described above makes it likely that the Earth will see glacial activity again at certain intervals in time. These cycles are known as the Milankovitch cycles, named after the Serbian mathematician Milutin Milankovic. He devoted much of his life to the study of the effects of these cycles on climate. If the Milankovitch cycles are set up for cool summers, then there is land near one of the poles, the stage is set for an ice age to begin. Milankovitch cycles happen more frequently than continental drifts, so one of these cycles is more likely to be the harbinger of the onset of the next ice age. The Earth has a landmass covering the South Pole and land masses surrounding the North Pole. It appears we're still in a warmed interglacial period. With all the variables in our time, it would strike one as essentially certain, and that relatively mild temperate climate we enjoy is but a fleeting moment in the vast span of geologic time, as we refer to as the ice ages. Thank you all for your time, attention. I'd gladly take your questions. This has been a fun and enlightening experience. Yes, sir.